Hello, thank you so much for coming to our paper in ACM Pack 2022, multi-stage screening, enforcing fairness and maximizing efficiency in a pre-existing pipeline. And this is the long version of the talk. This is joint with my amazing advisor, Avrim Blum, and my fantastic collaborator, Vakilian. So the motivation for our problem was thinking about fairness harms caused by scarcity. And in this case, you should think we have a small statistical difference between groups in a population as a consequence of some classifier trained on some data. But the difference is small. And where the fairness harm comes in is that someone is using this classifier to make an actual a decision with economic consequences and like economic stakes. So even though the difference is small, there is a noticeable difference you can get by like treating the groups differently. So you're going to, because you're like rational, quote unquote, self-interested, want to profit. And so we wanted to think about fairness harms of that type and how to mitigate them. And a scenario which we think that type of harm is plausible is thinking about this kind of hiring, pipeline, screening process. Typically in the paper we say screening processes, and we also call them pipelines. So let's talk about the model a little bit more specifically, and I think that'll make the high-level motivation a little bit more clear. So imagine you want to hire someone, and the very last step before hiring them is you have an expensive, like, on-site interview. It takes all day. You can only do finitely many of them. And so the primary goal of the firm initially is to minimize the expected number of interviews per successful hire. So the goal then is before you push people into these final round interviews, which like you have to do, you want to have a pool of mostly positive people that then you promote to that final interview. And so the way the pipeline works is there's that final expensive step, and then there's cheaper steps before it to get to that pool of mostly positives at the end. So the way one progresses through the pipeline is there's positive examples and negative examples. Like imagine there is a true labeling function. People really are good employees or bad employees. And then there's a sequence of tests. And you take the test, and with some Bernoulli, you pass the test, and that's captured by tau 1,1. And that's the case if you're a true positive. And with 1 minus tau 1, you fail. And if you're a negative, you pass the test with tau 0, and you fail with 1 minus tau 0. And in this case, tau 1 is greater than tau 0. So like for each pool of people who pass the test, there should be more positives than negatives. And then there's a sequence of such tests, and if there's enough tests, you're going to filter out most of the negative examples. And so going back to that fairness harm, like imagine each of the tests is sort of favorable towards like group A, two groups, group A, group A, group A, group B. And if you do enough of these tests, you could get like cumulatively a large gap or still even a small gap if I really care about minimizing those interviews. And at the very end, after all the tests, the group A pool is like 60% positive examples, and the group B pool is 55% positive examples. And I'm the self-interested, selfish actor. I'm going to pick only people from group A. And that's a fairness harm. And one response could be to impose fairness constraints on this type of pipeline. And we think about the constraints primarily evaluated at the end of the pipeline, but we also, in the paper, we also consider them for each step, which is probably not the right thing to do in this case, because in this interpretation, we really care about the outcome at the end. The intermediate steps are just a way you get to that outcome. And also the other thing to think about it is we think like the company controls the whole pipeline, but the company is fixed to using the test with these test parameters, the tau i's, and the taus are known to the company. The taus are known to the algorithm. They're like standardized, like taus have been developed. And what the company has to do is we're going to require this fairness constraint. Like, so imagine the government or maybe the company itself responding to this fairness harm. Says, all right, we're going to satisfy equal opportunity, have the same, give positive examples the same chance of getting through, for both groups from getting through the pipeline. And the action space of the algorithm is to modify the promotion probabilities in the middle. So like what that means is the test is fixed, but we're going to change how you use the test. So maybe we're going to promote everyone who passes the test, or maybe we're not going to promote everyone who passes the test. Maybe we'll promote only some of the people who pass the test. And so you have a promotion policy for the whole pipeline, which consists of how you promote people after each test. including to the very end, which is this expensive interview process. And the goal, again, here is to exhibit a pipeline that satisfies the fairness constraint over the entire pipeline, again, think equal opportunity, and is like an effective high utility pipeline from the perspective of an employer. And we're going to measure that in terms of recall and precision at the very end. So some complexities here is this is non-convex and pi. And I'll say that again a little later. So I'm just going to show you again our primary fairness constraint, which think now equal opportunity. So H here could, in general, is just a classifier, but in our context, you should think of H as getting to the very end of the pipeline, getting to the end of the screening process, taking the test and getting promoted through the test. And also note, like you could fail every test depending on the promotion policy and still get promoted. Or you could pass every test and not get through also, because the way we allow the promotion is it's randomized. So you take a test, with some randomized outcome, you pass or fail, and then there's another layer of randomization which determines whether or not you get promoted and move on. And so the tests just depend on group membership and your true label, and the promotion policies, the pies from the last slide. Let me show that again. The pies just depend on your group and your test outcome at that stage. So note, this pipeline here is just for one group, and there's another pipeline for another group that has different test parameters. And those different test parameters is where like the bias comes in. The bias comes in, or bias disparity here. The way we think about the bias is like in terms of that true positives from each group could have very different probabilities of getting the good outcome at the very end, which is getting hired. Okay. So just looking at the problem formally is summarizing everything I've said so far. The algorithm is given this screening process pipeline, P, with k stages, some number of groups X, and test statistics that capture how each test does on each group at each layer. And then the goal of that is to find these pies, pi x1, pi x0, layer J, for every layer for each group, such that the overall policy satisfies the relevant fairness notion at the end of the pipeline. So like you're matching the equal opportunity you're matching the recall for the groups, and it maximizes the given notion of what we call pipeline efficiency, which initially could just be maximizing precision at the very end, or a linear combination of precision and recall. And we call that pipeline efficiency. And so that's kind of our problem. And now I'm going to briefly discuss a highly abridged related work. So the first paper are the people who really initiated the study of fair pipelines. And I think that a very important paper then is these two works by Dwork and Avanto and ITCS, and Dwork, Avanto, and Jagadisan in 2020. So the first, again, very high level summary here. The first paper really explained a lot of ways group and individual fairness guarantees fail under composition. That's something that's also like observed in our work, like with the pipeline. Like this idea that fairness classifiers compose well is these first three papers really show that that is not true. And the difference between our papers and these from that perspective is we don't really focus on thinking about fairness properties composing. We're really focused on this fairness outcome at the very end, when the classifier is like this sequence of tests. So it's not like repeated classifiers. It's like tests that kind are combined to be like one big classifier. Looking at the next paper, Dwork, Avanto, and Jagadisan, we don't really have any of this cohort structure that they do. And some of their work focuses on like kind of separated design. Like some people have control over some parts of the pipeline, and you want it to like the whole cohort scoring rule to behave well. And so, yeah, we do not have that cohort adaptivity. The paper that we think is kind of closest to ours is this paper by Cohen, Lipton, Mansour in 2020, where how the tests give information is quite similar to ours. But in their paper, you're allowed to be hired early, and they kind of focus on some of the properties in making like the right decision rule under these different noise rates. versus we don't allow anyone to be hired early. You have to get to the end. So yeah, there's some fine differences between each of these kind of the last two papers in our setup that I think I'm excited to talk about with the authors, with people more, to really get a fine-grained sense of those differences. But yeah, so our model is distinct. And in praise of our model, I think our model is very general, and it's like very minimal assumptions and can be applied to sort of many screening problems. Okay, great. So just here's a little example pipeline where there's just one stage. And then we have the test parameters on the first line. So this means the test parameters here mean for group A, all the positives pass the first test, and so do half the negatives. And for group B, it means 80% of the positives pass the first test and 50% of the negatives. So looking at it really quickly, you notice that the kind of naive policy of only promoting people who pass the test does not satisfy equal opportunity. And P and Q are two different ways to satisfy equal opportunity. One which is kind of more forgiving, that promotes all of group B, so probably not a super useful test there. And P, which actually doesn't pass everyone from group A who doesn't promote everyone from group A who passed the test. In this case, only 80% of them. And we go on to show that P is actually the optimal policy that satisfies equal opportunity with respect to precision. And that holds in this example. And then we also show it holds on general pipelines in our model of case stages. So that's very satisfying because it's a very simple closed form solution for maximizing precision. And it's very natural. It's like just downweight your recall for group A to match the recall of group B. And it works for general groups too. Okay, so in interest of time, I'm going to kind of move through this kind of quickly, which is we also show that this example shows that the set of equal opportunity policies in these pipelines are not convex, and shows maybe some of the hardness of optimizing the pipelines for general linear objectives. Another negative result we have is kind of this non-locality of the optimal policy, where how you use each test kind of depends on all tests. And so it seems like you can't really get like a very simple greedy algorithm. So yeah, you have this like test dependence when we're looking at a linear combination of precision and recall. So this is kind of our very exciting theorem for when we want an algorithm that's an exact algorithm and it's exponential in k. We show, in words, we basically show that like the weak Pareto optimal policy, where the weak Pareto here means like the inequalities are greater than or equal to precision and recall. So like one of those is greater than or equal to, and maybe the other is equal to. There exists at most one fractional layer. And so that immediately gives you an exact algorithm because it's exponential, but you freeze the exact layer and then you search through the rest, which are non-fractional. So there's just two settings. So again, the issue there is it's exponential in k, but it gives you the exactly optimal solution. And it comes directly from this lemma. Okay, so, and we also exhibit a dynamic Harmon-based FP test. So just talking about general themes for a second. I think the two things I want to emphasize here is that like, I think post-processing and fairness, while in general, redesigning a system a priori to be fairness aware is probably better. You probably get higher utility, stronger fairness guarantees. Sometimes in practice, maybe post-processing is necessary and good, especially in the short term. And redesigning the system to be those more fairness aware is going to take much longer. And the other thing our approach is a start towards that I think other people are also thinking about is thinking about fairness harms contextually as caused and complicated by economic incentives. In a world with no economic incentives and scarcity, maybe fairness problems are much more tractable, while they can be complicated by these scarcity issues. All right, that's everything. Thank you so much for listening to the talk, and I'm excited to talk to you guys more in person at FACT.